Session for this afternoon. We have Annick Broussel, a research associate at L'École Polytechnique de Montréal. He works on performance analysis tool for Linux, Linux at Distributed Open Reliable Systems Analysis Lab, Dorsal, and is going to talk today on LTTng, which is going to be an advanced Linux tracing for everyone. Could you please give a very warm welcome to Annick Broussel.
Thank you. Just for a start, I just want to know who I'm talking to, just by a show of hands. Has anybody have heard about LTTng before? A couple of people. Who has used any kind of tracing tool, ftrace, perf, dtrace? So most of people. Is there anybody who know about nothing about tracing around here? No? Okay, so I'll go faster in the first slides. So as I said, I was working on LTTng with a bunch of people, mostly from Montreal, where it's currently nice weather and with a lot of snow. So enjoying here with the sun with you here. So, first problem. This is one presentation that one of my colleagues did a couple of months ago. He did a spatial view, or CPU usage view, and he compared like Firefox, Chrome, rendering the same YouTube video at the same time, and have a quick look at what's happening there. So we see a lot of XORG CPU usage over there, and what we found out is like Firefox was doing quite well, doing a bit of CPU usage, but at some point Chrome was like eating most of the CPU. By loading the tracing tool, this is the Eclipse view, looking at all the kernel event that was there, you're seeing that it was doing about every couple of microseconds. Chrome was doing a clock get time we don't know why, but it was filling the trace with all these events. This clock get time is a syscall event, and that we're eating up a lot of CPU time on that. So I don't know what exactly the problem with not a Chrome developer. So, but just to show you a little bit of what can tracing do for you, can pinpoint some kind of what kind of program your application are doing on your system. So, always get that quickly, but just to have just a quick review of if we talk a little bit of the same thing when we speak about tracing. So most people we see tracing a little bit of logging, but it's more level at a more lower level. And it's something that we use at a much higher frequency. As I've seen the event before, we can see event each microsecond and every 100 of nanoseconds. So you don't want to fill up like with text logs, something that is going that fast. So it's a way to see a little bit at specific point inside our system. So there's specific trace points in the kernel. They can be static or dynamic. So dynamic trace points are usually slower because you need to install them every time. You need to hit some special management, and where static trace points are really fast call that can get your data that you want out of the way quickly. So each trace point will go high speed, have a low latency. We usually get a timestamp, and we'll get some payload, some data you want to get out of your system. There's three main usage for using tracing. First thing, for like university people, students, learning about your system. It's a really good way to have an understanding of what your system is doing, what the scheduler are doing. We always learn about theoretical scheduling in our operating system courses, but when you get to an actual Linux system, it's a little bit more complex than that. So that's a really good way to understand what's there. I think most people are here to this part, the debugging part. We want to know we have some problem, and we want to see what are they found. The third usage that we commonly see is like event history. We have some partners that really want to just use tracing to just keep recording all the time what's happening in the system, and when they hit a bug, when there's some exception, some error that happened, they want to look, okay, I'll save whatever there's in my trace buffer, save that to disk, and do like offline analysis later. So tracing is really interesting for that because it doesn't have a big impact on your system. Wherever if you log everything on the text files, it can get quite heavy. So with tracing, you can get most data really quickly. So LTTng in all of that. There's a couple of tracing tools out in the market. So why we would like to add one? LTT has a quite long history. First started as LTT in '99. Got a big upgrade in 2005 with the first version of LTTng, LTT Linux Trace Toolkit Next Generation. By around that time, we've seen the dtrace and system tap appears, and a little bit later, ftrace and perf that are in the Linux kernel there. Last year, we released a new complete different version of LTTng. We call it 2.0. We kind of skipped completely the 1 version because it was so different and so awesome that we always directly go to the 2 number. And a couple of weeks ago, we released the 2.1 version. So LTTng, and what's the difference? It's a system that includes a kernel tracer and a user space tracer. The user space tracer is completely standalone from the kernel, doesn't need to the kernel, where System Tap also does both, but rely on some kernel instrumentation to do its user space magic. What do we have? What do we do differently with the LTTng? First thing, we started to aim, like we talk about tracing, it's a tool for kernel developer, and we're looking at like what is there, trace and perf was doing a really good job for kernel developer to get the information out. We take a little bit of a step back and see what we can do differently, where our tool can be used. So we look at, yeah, we'll do a tool for most of us, most of everybody. Well, not maybe all these people, but like everybody in the room, every software developer can be used. Still can be a useful tool for kernel development, but we like to provide tools that are useful for any user space developer, sysadmin, who want to really pinpoint their problem on their system. So the first thing we do is to get to an easy installation. Beforehand, we needed some kernel patches to install the kernel. Now we all remove the necessity on the kernel patches. You still need, it's only a couple of kernel modules. We support 2638 up to the latest kernel. If you need like to run on like Red Hat 6 system with to run the 2632, you need a couple of small patches to apply to your kernel and to make it running. We have a RPM package also for this already applied. If you need user space tracing and just want to trace your application, forget about kernel module, auto all run on user space, you can install it directly on your system. We are in almost every distribution, Ubuntu, Debian, Fedora. Fedora don't have the kernel module because of the policy of the distribution, but you can install it quite easily. Arch, SUSE, still pending on the Red Hat side, but should be in the next release of it. We support about every hardware out there, x86, ARM, PowerPC, Spark, MIPS. We are doing the port to the Tyler architecture if anybody is using that. And we are starting to do work on the new Xeon Phi, the many core architecture, because one of the goals of our lab is to like develop tools for like a lot of core systems. We do some work with 64 core computers. So we really want to have some system that scale really well at a high number of core. We did some port from other OS, Android, put it in the other OS category. Still, it's ongoing. If anybody want to help on that, we are really welcome any help. That side, quite interesting to plug additional module and additional daemon there. We did a port of UST on FreeBSD. It's out there, it's supporting the main line, and we did a prototype of a Sigwin port. We had a partner who wanted absolutely to do a demo on Windows, so we did that. Really painful, so we won't do it again. The other thing we did before, if anybody has used LTTng, the 0.x version was like UST has some specific command line, kernel was another command line, all different commands. So we did like rework all of that. We did like one simple command, LTTng, do whatever you want. We also have binding in C and Python, so if you want to actually do a control thing and a special surveillance application, you can do the control the tracing directly. So this is the standard command you'll use to do some tracing, create a session, enable some events, start, stop, you can view the trace and you can clean it up after that. One neat thing we did for, mostly like for sysadmin and maybe other usage, but this was the main focus group. we added the possibility for tracing the kernel by non-root user. So if you are a part of a special group, the tracing group, you can actually access the kernel tracer that way. We also support multiple sessions in parallel. What that means, you can create a session, activate a couple of trace points, do some tracing. You can activate yourself another session, activate other trace point, another user in your system that also has access to the tracing group, create another session, activate completely another set of trace point, and all these sessions won't interact with each other. So you won't, if you activate a trace point, you won't activate it on the session of the other. So we can debug your specific things, other guys can debug his specific things, and you will get each only the data you want on your system. How do we do that? A bit intro on our small, simple architecture. The main thing here in the middle, we have a session daemon that runs on your system you need to trace. That's where all the control magic is happening. This thing is interfacing with all the tracer. We have a module for the kernel tracer, and each of your application that has a probe in them that you have in them at compile time. When you start a session, all the application and daemon spawn, the session daemon spawn the consumer. His role is to actually get the data from the trace buffer to disk or to the network. We have a feature if you like doing the embedded development and don't have any hard disk there, you can just stream the trace network really fast through the splice system call. So it should be as fast as on the hard disk. So that goes to different storage. And you can after that use any view or UI that support our CTF, the common trace format for that. And you can control it with, as you said, with your own API or with the official command line tool. There's a lot of data, well, a lot of kind of data you can use with LTTng. I speak about the static trace point in the kernel. There's currently about 500 trace point available for tracing tools. It's all there for any tracing tool, Perf, Trace, System Tap, can all use them. LTTng support about a little bit more than, I say 2/3 of them, because we need to do some specific adaptation for them. There's things like scheduling, file system, block IO, network, and I forgot a lot of them. Via virtualization, also a lot of them have this. We can trace all the syscalls, so we can have an entry for every syscalls. So if you're used to using strace to get some syscall information, you can use LTTng to get the same information out of your system, and I'll show you soon that you'll get way better performance. We support kprobe in the function tracer. This is the dynamic instrumentation capability of the kernel, so we can just say, I want to trace this address, I want to trace this function, so you will see if you have a specific part of the kernel that you want to use is there. We have a thing which is the context, so to every event we can have what we call a context, which is like other information that you will get, like PID information, what's the current PID running. You can have all the performance counter, cache misses, and stuff like that, program counter, cycle counter, etc. That you can get there. So if you want to have an idea, like on every event, but you want to quickly see what was the PID running when I hit the system call or when I get this event, you can add that quickly by the context. What we also do in our analysis tools is we recreate a state system that rebuild the complete state of the kernel at any point in time. But if you want to do something quick, the context can give you the information. On the user space side, a little bit less there, but we have a static trace point with filtering, which so you can add your trace point in your application, and when you control the tracing, you can say, I just want to trace when this value is X, or like we have some font company that work with us, like I just want to trace this specific font call number. So when trigger this phone number, it will actually start the tracing and get some data. You can also add some context to the information there, like PID and stuff like that. It's all produced CTF data. It's a standard that was defined by the Multicore Association. Its goal to have the same format as other hardware-based tracing tools. So you can get the same information and the same tool to view all this form of data. For those of you who haven't have a look at what's a trace point, that's a kernel trace point. It's the sched process fork trace point. So every time you fork on the kernel, this trace point gets called if it's activated. So when you define trace point, if you ever want to add another one to some specific part of the kernel, all you have to do is write a small structure like that. What you have there is the prototype of the function. So you see what's the parameter that will get called to this trace point. What's the argument, the actual value. That's what will get written to the trace buffer. So you see that we'll write parent.com, parent PID, child.com, and child PID on the trace file. A couple of other stuff like just for like to assign, you need to specify to the trace point how you will copy data actually to the buffer. And in the end, it's mostly used by, I think ftrace, I don't know if perf use it, but it's how to convert your trace data to a text string. On the UST side, we did exactly the same thing, quite similar, just we had like a little bit different syntax. We have like a component domain, so we can classify your trace point easily by application. And we strongly suggest to people to like, if you have like your company name, a little bit like com.companyname.something, so don't clash with like org, Apache, HTTP, so we don't clash with other trace points with other application. And same thing, the fields, what's the type, what's the name of the parameter, and how do we store it in the trace file. To use it in your application, when you have defined it, simply call. You just need to do this call with trace point, what's the name, and what's your parameter in there. I was saying that tracing is quite fast. If just did a small comparison, so we did just I did a find on like 100,000 file on my system. Takes about half a second there. If I do it by running LTTng and getting all the system call information and all the event on the kernel, add about a second to it for the whole traces. If you do the same thing with running strace, it goes to about 40 seconds. So it's quite a useful tool if you want to actually have a less impact on your system to actually get real-time information and actually do some work, because it can get quite heavy to do. It's a good thing to use. We have a tool called LTTng that I'll demo shortly after that. So with a comparison of what's the total CPU time of running top for a specific period of time versus running the LTTng top at the same time. So we have a list impact on the system, and the interesting information is the number of syscall the top is doing to get your information. So about 250,000, and here on the LTTng is doing a lot less syscall. What we do, like top just like read proc file system every time you open all the files there, so open, read, close. Here we just like open the trace buffer, just stream the information there and close it at the end, so it's quite easy. And again, a less impact on the system. We did a little bit of comparison of with the competition with the dtrace and system tap on the user space side. System tap is quite better. I think this one was taking about a little bit over than a year ago, so system tap got better during that period of time, but still, UST, that's a nanosecond. So when you trace an event, that's the impact of one. So quite small, and on the big order of thing, between 250 and 500 nanosecond. That's for one thread. When it gets interesting, if you need to scale your application to more threads or more cores, we get in the cost and time on the UST side. We don't add more time if you're tracing 6 core, 1 core, 64 core. It's almost a constant linear time per core you add. Where the trace and system tap, it's not as the way they do the buffer is not as efficient for that, so it's get quite heavy. System tap doesn't have the same goal as LTTng, where LTTng really wants to get all the data out on the system, and you actually do the analysis after the fact, where system tap is really more geared to doing some script that will do the analysis online and actually just give you aggregated data at the end of your session. So how do you look at the data? Because you can get quite a lot of data. For about like 1 minute of tracing, it can get easily in the gig. So we have a lot of tools. First of thing, bubble trace, simply trace file to text converter or to other format converter. So you can see you have all the basic information. Timestamp, nanosecond precision, time difference between event, and event name, the CPU number on which was running, and all the data you have for this syscall. And a little bit of context information on this one, like which was the actual program running. So that's a basic tool we have. If you want to do something quick, look at some data, you can grep it, you can pass it. We have some nice script that does octing, and you can print it, the information you want to extract quickly. Quite heavy, but can get some information fast. I've mentioned the LTTng top. That's an N-curse program that aims to give you like a big overview of the information on your system, all the statistics, performance information, and all of that quickly on the command line, so it can easily be used like remotely through SSH if you need to debug some server out there. LTTv, which is my role to maintain. Simple C program, GTK, to view a trace quickly. I have the general component that we see in our trace viewer, like a control flow view where we see the state of each program, and like resource view, like CPU or RQ when they are using, and all the different trace data. Currently not available for LTTng 2.0, still trying to have it convert to the new CTF format. Quite an old program to support, so it's been in development for the last 10 years, so a bit of rework to do, but should be available quite soon. The main tool, I don't know if any of you use Eclipse, but if you do, you will be happy. If you're not, you will be less happy. But I mean, not an Eclipse user group, so that's why I work on LTTv. But it's quite a nice tool, really well integrated into your development environment, and it's really geared to have a more advanced analysis integrated inside it. Right now we mostly have the same control flow view, resource view, a lot of statistics. You can do even some control, remote control of your tracing directly to the Eclipse interface. What can be useful to do? The small script, small LTTng graph that use the Babel Trace API to actually extract some data information. Babel Trace has some Python binding, some C binding. So we can just, if you want to just do a quick graph of have an histogram of the event on the system to pinpoint when there was some problem. We did also, one of the students in our lab did some comparison to actually replace the system information that's huge CPU information, actually use tracing to get this data, so he has less an impact on the system. So that's the main tool. There are also a couple of commercial tools available. I know Mentor have some, I think Freescale support it also, so you can actually, they are mostly use Eclipse and rebrand it, but it's still a nice tool to have. So that's the current status, where we are going in the next months. That's what we will add. Live tracing. Right now, if you want to do analysis, you need to take the trace, stop it, and do your analysis. What we are currently adding, it should be in the next version in a month or two. It's live tracing, and it will be integrated into LTTng top, so we can actually just start your analysis tool, look at what's happening in the system, and get the actual information while you're tracing. The thing, we had the per user global buffer. It's mostly like an optimization on the UST usage. We have less an impact on the memory usage, because right now you need to have buffer for every application that use UST. So if you have a lot of UST supported application, that can use a lot of buffer. So we are adding this feature. Remote tracing, that's actually there. In fact, it's still there for an older presentation. So to trace on one system, send the data to another one. Filtering on the kernel side should be added soon. Now it's only on the user space side. Currently working on uprobe support. I don't know if you heard about it's added in the 3.5 kernel to have actually user space dynamic tracing, where you can just specify the address on any executable you have on your system and have some tracing tool happening. So we'll add that in the probably next version. And we also want to add some binding to other language. A lot of people are asking for Java binding for the tracing to have a better integration to the JVM. So we can just like have your Java application have some call in that, and instead of calling a GNI to get to the UST library, we'll do embed natively in Java. I work in a research lab, so we do a lot of things for the more future time, but like dependency analysis should be there in about less than a year. That's really nice tool that once we get out there are not yet available, but that will really ease the use of this tool and will give you the information more quickly on your problem. Dependency analysis is a tool where will show you the path of what is really blocking your application. If you have a web browser that do a request to a web server on your network and you trace all of these systems in between, it will actually be able to tell you like, okay, this web browser did wait on some socket request, but actually this other system, this other server, the server was waiting on some block IO or some network IO from a third server that was blocking some disk there. So we will actually be able to see the path of that. We actually have some demo of that on the lab. If you go to the website, we have some presentation on that. Multi-level event abstraction, like I'll show you too, there's quite complicated to see events, but like to show like, this is a file reading instead of like file open, read, close. We'll have like higher level event added to the tool so we can actually like see, okay, this is the general view, and after I can go deeper in my system to see the actual syscall. Time synchronization, if you like trace your whole cluster, or cloud. You might have some time difference between all your nodes, and since tracing is really precise event clock, you know a way to synchronize all of that. So we already have that in some older version, but we need to add that with the new trace points and all of that. And we're also working on using like the ARM, I don't remember the name, but there's some hardware tracing component there, so to core site, and get this information directly into LTTng, into CTF format, so you can see actually in the same trace. And I mentioned the cloud just because it's popular. And it actually gets us a little bit of grant money, so. So I'll do a couple of quick demo on the system, which I'll just play some demo. So that's just to show you the use of the command line, how it goes. So when you need to create a session, you can name it as ever as you want to different them. There's the automatic one. You enable some event. Now I enable every kernel event, every user space event. You start your session. You start your program you want to trace. Here's a sample, is a small program we have to do example that has some user space trace point. You can do whatever load you put in your system and you will actually see it on your trace. And when you're finished, you just stop the tracing and you can actually view the trace. So there's a neat, just an example of like, this is what we do, like we have a trace point in the loop called microsleep on every loop time. So we'll see what's the impact on the trace it has. So on the trace, you can see all the system call, the scheduling events, so you can see easily that the program was switched on and there. So if you look I will find just less fine to find my first user space trace point. Take some time because it's quite a big file, but we see here like the program was running on CPU 3. This was my message. This is the PID of my program. This is the timestamps. It's really useful like to find your user space event and to pinpoint it into the whole trace with the timestamp and to get it to the other tools. So what we see here is that if you look at the CPU tree, you see the syscall nanosleep that was called for the microsleep, and you see after that on the same CPU tree that's called the HR timer init and all the impact on the kernel after that. So that was for using the command line. You can have a look at the couple of command list that can show you like detailed information about your session, which tracepoint was activated, what's the parent. You can switch like the size of the buffers and all of that. So you can get, you can add more buffer, reduce the number of buffer, depending on what's your load on your application, what you need to, if you want to have a lot of trace point, less memory impact. And you see like there's like the M map, depending on what kind of output you can do, of what you can see if you do live tracing and all of that. You will see that into the list command. And when you finish, you can destroy your session and it's gone. You will need to start again. I'll go first to LTTng stop. This is a trace I've took before. I just like start tracing, go to Firefox, open start like a video on YouTube, and you just see a little bit of what's happening on the LTTng top side. So it's quite similar to top. You have like every process, PID, every thread ID, and their CPU usage. As you can see, by default, it goes over in time on every commit every second. And in the top, you see like the timestamp, and you see like how many threads were created and destroyed, and how many files were open and closed. Actual I/O usage file, I say file, but it's file descriptor, so it can be either socket, network, or all that. Interesting is you can like go forward in time, go faster, and what you can go backward. So if you want to analyze the system in your like startup, and wow, what was 2 seconds before? I forgot. So with that, you actually have the trace, and you can go back over there and see different things. You can sort the information. Yeah, you can sort by PID, by time, by name if you want. So here I sort by PID, so I can really find if I'm looking for one specific process that was causing some problem. Let's have a look at Firefox. So we see the PID and all its thread over there, and you can see the CPU usage of all of these, and we see that it was just the main thread that was doing some CPU. And we can actually hide the threads, so you can just show the main process and don't show the different thread. Other than that, you have a couple of other views that you can see. The performance top, which will actually get you the performance counter. When I added some context, so you can see the branch load miss, the major fault, the cache misses. On all the program, you can sort them, so you see that like, yeah, Firefox is doing a lot of stuff, doing a lot of cache misses. And you have an I/O version, so you can see which program does the most I/O on your system quickly, and sort them also that way. The other thing is that you can go directly into the data of one process, and there you can see what's its current CPU usage, what are the file open for this program, how many I/O each socket is producing. You can browse through them. You can go forward in time, backward in time for each process or thread on the system.
Top is dead.
So that was LTTng top. If I just go quickly to Eclipse to have a quick look. So that's not the same trace because there's a bug in Eclipse that don't like the context that are necessary for your LTTng top. But similar trace, I do the same thing. Like start a video around here, you see like the density of event are really higher that way, so you can like pinpoint, okay, there's probably something going on there. You can go there. You can filter by event type if you want like to see just some specific events, like you want to see all the exec where each program can start if you're looking for one specific program. And yeah, it's going to search all of that, and can go. You have all the same information as you had, like the argument of that. You can go back, you can zoom on any specific part of your trace, and you'll see that the histogram will move, the control flow view will move to all this you can synchronize. So if you can find the information, one specifically, you can like just select a part of it and have the statistics for just this part and find where the problem was, hopefully. So when you pinpoint a nice area, you can go to the control flow view that shows like each process, which all the state. Here we see in yellow is like just waiting, and in gray is like a mix of event. Blue is like, green is running actually on the CPU, and the blue is running in the system call. We have like, if you have a pop-up, you have the CPU number, and so you can go. There was nothing, a lot of happening over there, but you can, so it's a lot of processing, a lot of waiting. You can see here like running, syscall, running, syscall, so it was like reading some files or some socket. And other stuff. Here you see it was actually waiting for CPU. So now you see that, okay, there was no CPU available at this time. Is there any problem with the system for that? And actually, one interesting to see is like if you will show the CPU number, so you see that your process is transiting from one CPU to another. So that can be useful if you want to have some cache locality to debug, like, okay, is my application just like hopping around between CPU or staying on the same all the same time? Can be useful if you have some specific performance to do. So you can, other than that, there's a resource view with all the CPU and what actually each CPU is doing, which process is running in each CPU, and some statistics. So that was the most interesting part of that. So I will be open to any question. So if you have any question on the project, if you need to contact me, information is there.
All right, thank you very much, Anik. Very good, huh? I suspect we may have a question or two. Yes, one right at the back there.
The interactive stuff you were doing there, if you're not an Eclipse user, is there an equivalent outside of Eclipse?
Yeah, there's a LTTng, which should be available in a couple of weeks, but does about the same thing in the more simple environment, because yeah, we are aware that not every person wants to start Eclipse on their system or can on 12-inch screen, quite not fun to do. So, yeah.
So I'm running on 2632. If I want to just trace user space, I can do that?
Yes, you can do that. There's no problem. The limitation is only, I think we need at least 2616 for some of the component, but for you have no problem for user space tracing.
So you're talking about the option of underprivileged users tracing via being in a tracing group?
Yeah.
And I'm just wondering what provisions you've got to prevent those underprivileged users from tracing data that they might use to elevate their privileges further.
For the one in the tracing group?
In the tracing group, yeah.
If you're in the tracing group, in fact, you're as the privilege as root. You can trace everything. So you might have access to some unprivileged data, so you need to really be specific on who you put on this tracing group, because you can have access to any kernel event.
So essentially you may as well get that person sudo to root.
Yeah.
Anyway.
Yeah, just a simpler way to manage it, but...
and that is for user space tracing as well, is it?
Yes, it's applied to user space tracing as well. As a user, you can trace all your applications, and not everyone, not the other one, but if you're part of the tracing group, you will be able to see the other users' applications.
I hate to be the one to ask this, but what do you think the chances are of LTT ever going upstream? Sorry.
I was expecting this one. I think it will get there someday, probably not this year. There was some discussion last August at the Tracing Summit about maybe have some, not merging, but using something between ftrace and LTTng. We really find that, we discovered that perf has really different use case, and it might have some, it's more like sampling than tracing. So it might have a use case for 2 tracers in the kernel, 3 might be a little bit more than 1, but what we're building is we want to build a user base and probably get there at some point. But there's some work we can do with the ftrace people to merge that there.
For system call tracing, like a strace equivalent, do you need the kernel support or?
Yes, you need the kernel support to trace all
So that means it's not available for 2632. You need to patch the kernel.
Yeah, you will need to patch. Yes. I don't know if we might be able to do something just for the syscall, but I'm really not sure if we can do it. But that's something we could look into. Maybe if we just like extract just the syscall, we might book somewhere else and do it. If there's a demand for that, maybe it's something we can look into it.
Any questions that are not in the top right of the auditorium?
How stable is the kernel module? Is it going to crash my production boxes?
No, it's really stable. We are really focusing we want to have you run that on your production system, and we have like partners that running that on production system. So we are really like strict on the stability of that.
That's great. That's the first question they'll ask me next week.
Yes.
You talked about adding trace events to Java. Are there other programming languages you're looking at adding trace events to, like Python?
Python would be the other one that the person I would want to look into. It's quite interesting. I don't know how we could like maybe build something into the interpreter there to have some nice trace event. I did some demo last year about like to do a small Python component, and I did a trace of like I did some trace event in HTTPD. In MariaDB and in some Python CGI, and you can see all that user space tracing, even with the kernel tracing, all that. So right now you can do it easily with like the C bindings, but it would be interesting. And we have a lot of the demand for Java, but Python would be kind of the next step over the year. If there's some people who want to work on that, we are really welcoming contribution.
Okay, I don't see any more hands, so can we please put our hands together for Annika Bouchard? Merci beaucoup, and très bien. And that's from the Linux Conference.